We're talking concrete today, and we're not just talking the square, little, beautiful, perfect, rectangular, easy concrete beams. We're past that. We're stepping it up a notch. We're getting close to the PE. We're close to the end of year exams. So we're taking it past the little baby geometries, and we're going to T-beams. Oh yeah, and I'm talking neutral axis outside of the flange. What the heck is he talking about already? Don't worry about it. We're gonna learn it all. Big announcement, we actually just partnered with Brave Browser. If you're like, what the heck is that? It's an alternative Internet Explorer option, and for all you cryptocurrency savvy teammates out there, you know what the dealio is. If you'd like to tip this team, it would be greatly appreciated, but obviously totally cool if not. I'm just learning it myself. If you don't know what the heck's going on, just let it fly right by. It's fine. Jose does it all the time. All right, let's jump into the classroom, shall we? Ta-da! T-beams. Scary as a rib slab system has the dimensions shown. Each beam uses 3 number 9 longitudinal bars. The concrete has a compressive strength of 3,000 psi, pounds per square inch. The steel has a tensile yield strength of 60,000 psi, pounds per square inch. Determine the ultimate moment capacity of this design per repeating unit. You're like, whoa, wait a minute. I don't see any multiple choice answers. I'm skipping this problem. You're crazy. Hang on. I'm stepping it up just a little bit here. This is kind of a hybrid between just your typical PE problem and a problem you'd see in real life or in an engineering, design of concrete class, advanced concrete class. So we're opening up the gates for everybody here, okay? But you could see a component of this on the PE exam. So where to begin here? Well, first I would say it's per repeating unit. And you're like, well, what the frick? Per repeating unit just means boom, boom, per T section. So because we have 34 inches on center for the webs, these guys are the webs, we know that it's carrying some tributary area that would be like this per web, which creates then your T section. But check this out. We have 34 inches between each web. So say not drawn to scale here, so just keep that in mind. And this slab is only 2 inches. So you might be thinking, well, is that entire 34-inch tributary width an effective part of our T-beam? Do we get to use all of that? Well, there's actually the ACI that's going to tell us whether we can or cannot. It has guidelines. So let's flip over to that. Here we are, gang. Chapter 9, I would say that this is the chapter for beams, like it reads right there. And we're dealing with T-beams. Makes sense so far, right? Don't overcomplicate the ACI code, because the code itself is already way too freaking complicated. What do you know which chapter is for beams? Go to the front where they have all the chapters listed. What is it, the index? Honestly, I totally forget. I don't know how books work anymore. Go to the front. Now, if we scroll down, we start to look, because we have a T-beam, right? I don't see anything on the front here, so we're going to flip over. Hey-ho! Okay. 9.2.4 T-beam construction. I like it. We're in the right area now. And then we are looking for, look at this, 9.242. Effective flange width shall be in accordance with 6.3.2. That's what we're looking for, our effective flange width. We are now in chapter 6. Honestly, I don't even know what chapter this is off the top of my head, but this is where we're supposed to be. And you can see 632 is T-beam geometry. I still like it. We're in the right spot. We go down a little further. If we dump into this table, you will see dimensional limits for effective overhanging flange width for T-beams. And that is literally, if you were to consider the concrete T-beam as like a wide flange steel section, we call the flanges, we know what the flanges are defined as. You can call the T-beam, the horizontal portion of that T, you can call that the beam's flanges, okay? Which is effectively just that portion of slab that sits on top or is cast integrally with the concrete beams below. And it gives you this little table here. So, flange location, each side of web, And we have effective overhanging flange width beyond face of web. And the least of 3 options, 8H, SW over 2, or LN over 8. And in the paragraph above, they define what each of those are. H is the slab thickness, and SW is the clear distance to the adjacent web. And then L sub n is the length of your span. So let's jump back and let's write all these constraints down, okay? And we will plug everything in, and then we will see what the least value is, and we have to use that per the ACI code. It'll make a lot more sense when we draw it out. See you back there. So 3 options. We have 8H, we have SW over 2, and we have L sub n over 8. Well, we weren't given criteria for the span of our T-beam, so we can't do this one. So we can't figure that one out. So that one can just be crossed off right away. But let's try 8H. So H is the thickness of your slab, which is 2 inches. So 8H is going to go to 8 times 2 inches, which equals 16 inches. And this is the distance on either side of the web, okay? So this now is 16 inches, SW over 2. That is the distance from the center line from web to web, which is this pretty little number right here, 34 inches. So this is 34 inches divided by 2, which gets you 17 inches. And then we know, obviously, that one is just nothing. So we need to take the least of our options here, which is 16 inches. So that means our effective width, BEF we could call it, is going to be, if this slab kept going type of thing, is going to be that dimension, which is just going to be BEF is going to be equal to 16 inches on either side. So 16 inches plus 16 inches plus the thickness of your web, which is 10 inches. That is right there. That gets us 42 inches as our effective width of our flange that we can engage, okay, and use when designing and figuring out the capacity of our individual T-beams. Well, 42 inches is greater than the spacing of the webs on center, which is 34 inches. So we know that we get to use the entire portion of the web that we have. So we could use a maximum of 42 inches. So if the webs were actually 42 inches apart, we could engage and use that full dimension. If the webs were 60 inches apart, we couldn't use that 60 inches. The maximum we could use would be 42 inches. Okay? But in our case, we are spaced at 34 inches. So obviously, we can't use 42 inches because all that's there is a maximum of 34 inches. So effectively, we got this going on. Hopefully I draw it well enough. We got this guy going on. Not to scale, okay? Get our rebar in there, beautiful rebar. And we have that dimension is 34 inches, and we get to use all of that. 2 inches, 10 inches, we know that's 12 inches. All right, there we go. Let's fly. Next, we know what our steel is in this thing. We know that it's 3 number 9s. Area steel for your size bar, that's in your ACI manual in the back, as well as, look at this, right in front of me today because I was using it, your student detailing card from Chrissy, all the way back from college. You can get this online and just print it out. This has all of your bar sizes as well. So a number 9 bar, area steel is 1 square inch per bar. So that's 1 inch squared. We have 3 bars. So that's 3 inches squared of steel that we have. And we know that Fy is 60 KSI. So that means that our total tensile capacity of our steel in our T-beam, T is equal to ASFY, which just equals 3 times 60, which equals 180 kips. So that's good. Next, we want to find our compression block, right? So if we go back up here, now we want to know if we were just to have a rectangular beam, you know, the real easy suckers, we would say, okay, now we have your tensile force, but we know that your tensile and compression force need to counteract, they need to equal one another in order to have a balanced system. and have internal equilibrium within the beam. So we need to find our compression block. But it's not so simple because it's not a perfect square or rectangular shape. It's this weird T geometry. And do we even know if the compression block looks like I've drawn it? Like, what if we did green here, what if that block is actually just all chilling up in the flange and it doesn't even make its way down into the web? Like, I don't know. And you're looking at me like, yo, Rich, I don't know. You're telling me right now. Like, which one is it? What are we doing? Okay, let's walk it through. It can be pretty straightforward. So we know at least you have C and you have T, and they're equal and opposite. C equals T in order to have a balanced system, to have internal equilibrium. And we all know the equations still apply. So C equals 0.85 F prime C, and then you would do like A times B and blah, 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 and you'd find A and do all of that stuff. But because we have a weird geometry, we don't yet have an equation to solve for our area of our compression block. So we're just going to define it as A sub C, just the area required. With these three equations, what was that, mathematics? Was that Calc like 1, 2, 3, or 4? I don't even remember. Hardly use them anymore. Calc 1 I use. But you have three equations, so that means you can solve for a bunch of stuff or something like that. I don't know. Don't at me, okay? All you math majors out there, all nestled inside your seats. I don't know which ones are you, but I'm not going to go that far into the mathematics of it. Sorry. Not sorry. So we're going to use these three equations in order to find what we want to find, because we know that we can rewrite it as ASFY, which is just T. We can substitute that in for C, and that's going to equal 0.85. Your F prime C is 3 KSI, or 3,000 PSI, AC. And obviously, we know what T equals. We solved it above. That's 180 kips. So we can solve for everything to find what the value of A sub C is. All of that jumps out, and A sub C just equals 70.6 inches squared. This is an area again, right? We have kips and we have KSI, which is kips per square inch, so our answer is going to be in inches squared. Make sure you're just keeping all the units, doing a check, okay? You don't want to mess that up. And of course, we're solving for an area, so you know it's going to be inches squared, feet squared, meters squared, something squared. That's a distance. Just I know it's all so repetitive, and you're like, come on, Rich, we're better than this. You just want to make sure you're getting the bunnies, Okay, so that is the amount of area in our compression block that we need. Well, now a little fun trick that we can do is this. Again, I'm going to keep on not drawing these to scale at all. Well, we already know what the area of our flange is. So let's first see, is the area of our flange, if that is equal to or greater than AC required, then we know that the neutral axis falls within the flange itself, and that compression block never slides in down into our web. Okay? AF, for area flange, is just equal to 34 inches times 2 inches, which equals 68 inches squared. That is unfortunately less than A sub C equal to 70.6 inches squared. So that means we do not have this case, and we do actually have the compression block sliding down into some distance of our web. But that's okay. Don't panic. This is the one that's more challenging. This really just drives it home, because if that compression block was just all in your flange, I mean, look at this. It's just a rectangle. So then from there, you could just solve the equation the rest of the way with the formulas that you would use for a typical concrete rectangular beam. Simple, easy, done, we're out of here. But in this case, we're not there yet, so that's all right. Well, how much into the web from the underside of our flange do we need to go? That, again, actually is pretty easy to solve. We're going to erase the X, or the question mark, and we're going to call that X, okay? We can keep this simple just through summation of areas, okay? So our compression block that we need, A sub C, is 70.6 inches squared. We know that the flange is 68 inches squared of that area. So if we subtract that out, that leaves us with 2.6 inches squared remaining. So that's how much area we still require. Well, we know that the width of our web is 10 inches. So we have an unknown, right? Because we just need, I'm going to draw it in green, we need to know how much this area is. And if we already know this dimension, we just need to know this dimension. So we can just write this equation now. 2.6 inches squared equals x times 10 inches. So just divide that by 10. X is going to equal 0.26 inches. That's how far down our neutral axis comes. Okay, so we know our compression block geometry. Now, let's find the capacity of this member, shall we? Well, how are we going to do that? Before, when we just had a rectangular beam, and we had some area steel in it, and then we have some compression block up here. This is A. This is D to your steel. You know that phi mn is going to equal, in this case, phi is going to be 0.9. It could slightly be different, I know, but times T, this being T, which is equal to ASFY, and you have this being C, which is equal to 0.85 F prime C. This is base width. Base width. You would just do 0.9 T times D minus A over 2, because that is your internal moment arm. Boom, boom, between these suckers. And that would get you your moment. But this time, like I'm saying, draw it in green here, we do not have a perfect square / rectangle. It's not that easy this time. We got some fancy pants geometry that I swear I never, ever, ever draw to scale any single one of these attempts. Not even close to what it looks like. We got this scary Jimbo. Well, what are we going to do with it? Because we still got something very similar. You got the steel down there. That's T. And this is, the rest of your member. But you have C up here, but where does that compressive force live? Where is it in here, huh? Is it, I'm going to go blue. Is it up here? Is it down here in green? Is it black? Is it right here? We don't know where it is, but we need to find that. And how do we find that? Because ultimately, we need to find this distance, this moment arm. And in order to find that, we go way back to the basics. We have a geometry, and we need to find the neutral axis of that shape. So let's go a bit further here. I'm going to redraw. Nope, didn't do it. Didn't do it at all. Didn't even come close to scale. And we're going to split this up into section 1, into section 2. I know you're all just loving this right now. You're like, oh God, flashbacks. And we're going to go from the top here. I'm just going to call it the x-axis, and we're going to go down. And we need to find y bar. That's what we're looking for here. And we know all our geometry, right? It's easy. 2, 34, 0. What did we say? 0.26 and 10. Okay, so this is easy. Y bar is equal to A1, Y1 plus A2, Y2 over the summation of A. If you don't know that, drive that home. Write it in your ACI, write it in your notes 24/7. Just write that equation on a piece of paper every time you do your homework for these classes. Write it in your steel manual, all right? It should be in there. It's just one you always want to know off the top of your head, because you're always going to be using that, especially in the professional field. A1 is equal to 34 inches times 2 inches. And y bar 1 is just to the centroid of your A, drawn green, of your A area from the axis that you started on, which was up top here, so from the top of the flange. That is just 2 inches deep, so to the midpoint of that is just 1 inch. So 1 inch plus A2, which is the blue area, that is 0.26 inches times 10 inches times the midpoint of this from the top flange, which is 2 inches for the thickness of the flange, and then half of 0.26 to get to the midpoint of the blue square. That is 2.13 inches. Divide all that by 34 times 2, because that's A1, plus 0.26 times 10, because that's A2. That equals 1.04 inches from the top. Now, we can find phi mn. Phi being 0.9, T, we know, is AS Fy, which equals 180 kips, times D, which is just 12 inches, minus Y bar. Y bar being 1.04 inches. All of that equals 1,775.5 kip inches, because it's in inches and kips right now. So if you divide by 12, that will turn it into kip feet, which is 148 kip feet. That is the capacity, the bending capacity of your T-beam. That's simple. Knocked it out. Look at all you. No one's sweating in this classroom right now. I'm looking at all you up here. You're looking good. You're looking real good. We're killing it. Let me know if you have questions, obviously, in the comments below. Send me an email. All the interaction has been really, really fantastic. Again, if you like this content, if I answered some of your questions, if I made it a little easier for you, subscribe, stick around. Let's chat a little bit more. Like the video if you haven't yet, and only if you want to, though. And if you are part of that Brave Browser Network and you're a crypto guru, send a tip for Rich at Team Kestava so that we can take it and put it right back into the classroom. I'm talking leather seats, I'm talking new projectors, I'm talking popcorn machine maybe a vending machine of some sort. I don't know. Let's get crazy, let's talk it over, let's see what this group wants, let's see what the team wants and needs so that we can all move the hell up and succeed a little bit more every single day. This is Rich with Team Kestava. I'll see everybody next time. Later.